Hey guys, good evening and welcome back again to your Unacademy NEET English channel. I hope all of you are doing great, having a good time. So my dear students, quickly let me know in the chats if all of you can hear me, if I'm perfectly audible and visible to everyone. Good evening people, good evening and welcome back. Good evening and welcome back. Just quickly let me know in the chats if all of you can hear me, if I'm perfectly audible and visible to every one of you. Quickly in the chats. Yes, audible, visible? Perfect, guys. So, as you all must be knowing, today it's going to be our fourth session of the chapter Atomic Structure, right? If you remember in the last session, we discussed Bohr's theory basically, and that was the detailed discussion of the Bohr's theory. I hope every one of you have watched that particular session. And my dear students, what exactly I'll be talking about in the today's session? What all topics I'll be covering in the today's session? My dear students, today our target is going to be the complete hydrogen spectrum in detail, number one. Number two, we shall be discussing about de Broglie's hypothesis. That is going to be the second topic, all the problem patterns of it, right? And the third topic is going to be your Heisenberg's uncertainty principle. Yeah? Your third topic for the today's session is going to be Heisenberg's uncertainty principle. So all the three topics which I'm going to cover today, they are very, 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 very important, my dear students, because questions have been frequently asked from these topics, and I would want you guys to take a note of every single thing, whatever I'll be mentioning on the screen in the today's session, because every single point is going to be equally important. Okay? And at the same time, as I told you a few days back, one session related to the Avengers 3.0 batch launch, right? My dear students, this batch is getting started on 21st of this particular month. So all the students who have not enrolled into this particular batch yet, Avengers 3.0, which is particularly for all the NEET aspirants, in which your whole syllabus is getting completed in physics, chemistry, biology, right? With the test series, all the chapters from the basics, chemistry taught by me and HSP sir, physics by Shreyas sir, bio by Ambika ma'am, right? So the ones who have not enrolled into it yet, do get enrolled as soon as possible. The link is there in the description box of the same video which you guys are watching right now. Okay? I'll be talking more about this particular batch after some time, right? After completing certain topics, I'll be talking about this particular batch in detail, right? Perfect, guys. So, are you all ready for the session? Are you all ready for the session? Are you all ready for the session quickly? All ready? Good evening, good evening. Welcome back. All right, people. So, our first topic in the today's session, which we are going to discuss right now, what is that going to be? That is going to be spectrum. My dear students, this particular term spectrum, I'm sure all of you would have come across this particular term spectrum. Let's exactly get to know what the spectrum is all about and what all things we have to remember in this particular spectrum. My dear students, spectrum is defined as, the collection of radiations of different wavelength on a photographic plate. The collection of radiations of different wavelengths on a photographic plate. What is meant by it? How can we understand this particular term? Let's have a look, people. Let's have a look. For example, just to make you understand, let's say I'm taking a prism over here. Let's say this is the prism which I'm taking over here, right? My dear students, let's assume that I have got a white light. Which is incident on this prism. This is your white light, for example. This is the white light which is incident on the prism. Now, what this prism is exactly going to do? This prism is going to split this white light into 7 different colors. You know that. This prism is going to split the white light into 7 different colors. Perfect. 1, 2, 3, 4, 5, 6, and let's call this as 7. This prism is going to split the white light into 7 different colors. And I'm sure you all know what colors these are exactly. Right? This is your, for example, violet, indigo, B, G, Y, O, and R. Perfect. This prism is going to split the white light into 7 different colors. Right? Or I can say it like this. The prism is going to split this white light into 7 different wavelengths. These are 7 colors basically, and every color has got a particular wavelength over here. Red will have a particular wavelength, right? Orange will have a particular wavelength. Yellow will have the particular wavelength. Every color over here, every radiation over here has got a particular wavelength basically. Now, my dear students, imagine that I have kept a photographic plate over here. This is a photographic plate which is dark in color, right? It is dark basically. It's a photographic plate. Now, my dear students, what exactly you are going to see on the photographic plate? When the white light passes through the prism is going to split it into the 7 different colors, 7 different wavelengths, and over here on the prism, right here you will see a red spot. Right here you will see orange spot. You will see yellow spot here. Here you will see green spot. Here you will see blue spot. Here you will see indigo spot. And here you will see the violet spot. Right? So can I say I got the radiations of different wavelengths on this photographic plate? Absolutely, I got the radiations of different wavelengths on this photographic plate. And my dear students, what is a spectrum basically? What is a spectrum? It is the collection of radiations of different wavelengths on a photographic plate. So over here I had taken a photographic plate, and on the photographic plate, what did I get? I got the collection of radiations over here which have got a different wavelength. And let me tell you the collection of radiations of different wavelengths on the photographic plate. This collection is something which you call a spectra. Or in simpler words, in very simple words, if I need to explain spectrum, if I need to define spectrum is basically the image that is getting formed on the photographic plate. Right? In simpler words, just to make you understand. Yeah? It is basically the image which is formed on the photographic plate when the radiations of different wavelength, they fall on this particular plate over here. I hope you got the idea of what the spectrum is. So what is the spectrum? It is the collection of radiations of different wavelengths on the photographic plate. Or in simpler words, the image that gets formed on the photographic plate. That's it. Right? My dear students, just tell me one thing. Will this photographic plate right now, will it look colored? Absolutely, this photographic plate will look colored to us, right? Because over here, there will be a red spot, orange spot, yellow spot will be here, green spot will be here. So this photographic plate, it will look colored to us basically. If you look at this photographic plate, it will look colored to you, right? Why? Because the radiations of different wavelengths have fallen on this photographic plate, right? And the image which has got formed on the photographic plate, that's something which you call a spectrum basically, okay? Now people, the spectrum which we are talking about, the spectrum, the collection of radiations of different wavelengths on the photographic plate, that's what you call a spectrum. Now people, this spectrum, we are going to classify into 2 types. This spectrum, I'm going to classify into 2 types. One is called as absorption spectrum. One is called as absorption spectrum, and another one is called as emission spectrum. Now, what this absorption and emission spectrum exactly is all about. Let's try to understand this in detailed format, right? First thing, my dear students, absorption spectrum, let me tell you, absorption spectrum, it corresponds to the absorption of light. It corresponds to the absorption of a radiation, I'll say. Absorption of a radiation. And this particular emission spectrum which we are going to discuss, it corresponds to emission of radiation. It corresponds to emission of radiations. Now, what it means exactly? How can we understand this? Let's try to say exactly. See, guys, for example, I have got a source of white light. Let's say I've got a source of white light, which is emitting basically white light. So in short, let's say this is the white light coming from here. This is the white light coming from here. This is the white light coming towards this particular direction. Now, my dear students, imagine that I have taken a container, and this particular container, imagine that it contains a solution over here. Imagine that it contains a solution over here. Perfect. Now, my dear students, what exactly is going to happen when this white light is going to pass through the solution, right? When white light is going to pass through the solution. After that, the white light which is coming out of the solution, I'm going to make it fall on the prism. So what exactly is going to happen? The white light which is coming out of the solution, right? When it will be incident on the prism is going to split this white light into different colors. And over here, what exactly I'm keeping? I'm keeping a photographic plate over here, which is basically dark right now, okay? Now, for example, I'm assuming one thing. Understand. Since this white light, it consists of 7 different wavelengths, right? This white light, it consists of 7 different wavelengths, correct? 7 different wavelengths. Now, let's assume that when this white light goes into the solution, let's assume that out of 7 different wavelengths, let's assume the solution absorbs 2 of the wavelengths. Let's assume that the solution which I've taken in the container, it absorbs 2 of the wavelengths. So first of all, how many wavelengths we had in the beginning? 7, right? V, I, B, G, Y, O, R, right? For example, I'm assuming this particular solution is absorbing your blue radiation and green radiation. Let's assume that. Let's assume this particular solution, it's absorbing blue and green. Perfect. Now imagine if there were 7 different wavelengths in the white light. Now the white light passes through the solution absorbs 2 of the wavelengths. Now, my dear students, the light which comes out of the solution, how many wavelengths it will contain? It will contain 5 wavelengths. Basically, right? Now, this particular light which is coming out of the solution, which contains 5 wavelengths, I'm making this light incident on this particular prism. Now, what this prism is going to do? It is going to split this light into how many colors? It's going to split it into 5 colors now, because there are only 5 wavelengths. But what is exactly happening? Try to understand. So what exactly is going to happen? Let's say this is your, just a second. Okay. So this light which is going into the prism is going to split this light into different colors. One is going to be violet, V, I, B, G, Y, O, R. This is what prism was supposed to do. My dear students, this is your violet, right? When this particular radiation falls on the photographic plate, when this particular wavelength falls on the photographic plate, what you'll observe? You'll observe a violet spot over here. Similarly, this was supposed to be your indigo. When it falls on the photographic plate, you will get a indigo color over here, right? Over here, it was supposed to be blue. But blue is absorbed by the solution, right? So basically, blue was supposed to be here somewhere. But instead of blue, you will find a dark spot, because blue is already absorbed by the solution, right? So this is VIB. Now, this was supposed to be green. But green is already absorbed by the solution, right? So on the photographic plate, there'll be one more dark spot. It was supposed to be green spot here, but it's going to be dark because green is already absorbed with the solution. Perfect. So this is V, I, B, G. This is Y, yellow. This is orange and this is red. So basically over here you'll find a yellow spot. Over here you'll find the orange spot. Over here you'll find the red spot. Perfect. If you look at the photographic plate over here, this is violet spot, indigo, dark spot, yellow, orange, red. My dear students, can I say on the photographic plate, I got dark spots on the colored background? Absolutely, I got dark spots on the colored background. So first point which you are going to remember over here, in case of your absorption spectrum, you get dark spots on the colored background. You get dark spots on the colored background. Now the point is, why do we get these dark spots on the colored background? Why do we get the dark spots on the colored background? That's your question. My dear students, what happened exactly when this white light goes into the solution? Right? The solution absorbs two of the radiations. One is blue, one is green. The solution absorbs two of the wavelengths, blue and green. Now, my dear students, solution consists of atoms basically, right? And in the atoms, what do we have? We have got electrons. What is this blue and green basically? These are the radiations which will be having certain energy. So I must say the atoms in the solution, they are going to absorb these two energies. They are going to absorb the blue radiation, green radiation. They are going to absorb this blue wavelength, green wavelength, right? They are going to absorb these two energies over here. And my dear students, you know, when energy is absorbed by the atom, what happens? Electron moves from low energy state to higher energy state. So basically, these are the wavelengths which are basically absorbed by the electrons in the atoms of this particular solution. So these wavelengths are absorbed by the electrons in the atoms. And you know, when electron absorbs energy, what it does? It moves from low energy state to higher energy state. So can I say these two wavelengths are used for the excitation of electron? Yes. Can I say these two wavelengths are used for the excitation of electron? Perfect. So these two energies have been absorbed by the electrons in the atom. So what has happened? When the electron absorbs energy, it moves from low energy state to higher energy state. So these two wavelengths have been used for the excitation of electrons in the atoms. Right? That is the reason why you got dark spots over here. It was supposed to be blue and green, but it won't be blue and green here. These will be dark spots here. Perfect. So whenever you see such kind of the spectrum where you have dark spots on the colored background, this photographic plate, the image formed on the photographic plate right now, which consists of dark spots on the colored background, this is something which you call as the absorption spectrum. I hope you got the idea of what this absorption spectrum is all about. Now, let's talk about the emission spectrum. My dear students, emission spectrum, it corresponds to emission of radiations. Right? It corresponds to emission of radiations. Now, for example, let me write one statement over here. I'll say a source of light. Let me write it like this. A source emits the light. Which falls on the prism. Which falls on the prism, gets splitted into different wavelengths. What does this particular statement mean? Before talking about this particular thing, let me tell you, your source of radiation, it can be anything. It can be bulb. Your source of radiation can be bulb. It can be sun, right? It can be your excited atom. So the source of radiation, first of all, The source of radiation, first of all, it can be your bulb, it can be sun, it can be excited atom. Now try to understand it like this. Let me erase this part. Try to understand like this. Let me make it very simple for you. My dear students, over here, if I talk about the atoms, can I say atom has absorbed blue and green, due to which what has happened? The electrons in the atom, they have got excited. Absolutely, they have got excited. Now you must be knowing electron in the higher energy state, it is considered to be very less stable. Electron in the higher energy state, it resides only there for 10 raised power minus 8 seconds. When the electron goes from lower energy state to the higher energy state, because of the absorption of energy, the electron in the higher energy state, it just resides there for 10 raised power minus 8 seconds. Because electron in the higher energy state, it's considered to be unstable. So what will happen? No doubt, the electron absorbed the wavelengths over here. It got excited. But in the excited state, electron is very unstable. So it is going to jump back. Now, my dear students, when the electron jumps back from the higher energy state to the lower energy state in the excited atom, when the electron makes a transition from high energy state to lower energy state, can I say it's going to emit the radiations? Right? It's going to emit the radiations. Now, my dear students, let me tell you, it is going to emit the same radiations which it had absorbed over here. So if I ask you now in case of emission spectrum on the photographic plate, will you see all the 7 wavelengths? Will you see 5 wavelengths? Or will you see just 2 wavelengths? You will just see 2 wavelengths. Which all wavelengths? The wavelengths which the atoms absorbed over here, right? One is going to be your blue, and one is going to be your green. Perfect. So over here, if you look, this is a blue colored spot. This is a green colored spot, for example. Can I say on the dark background we are seeing the colored lines, right? I can say in emission spectrum, what happens? What do we get? We get colored lines, or we get colored spots. On the dark background. And my dear students, whenever you see this kind of the image, on the photographic plate, wherein on the dark background you have got colored spots, this particular image, this particular spectrum, which corresponds to emission of light, this is something which you call as emission spectrum. Perfect. So first of all, what happened? This solution absorbed 2 of the wavelengths, right? By means of which electrons got excited. Electron in the excited state is considered to be unstable. It just resides there for only 10 raised power minus 8 seconds. So it jumps back from higher to lower. It's going to emit the same radiations which it had absorbed, right? And those 2 wavelengths I'm showing over here on the photographic plate. Yes? Perfect. So what did we observe on the photographic plate? We observed colored spots on the dark background. Whenever you see such kind of the image on the photographic plate, wherein you have colored spots on the dark background, this particular spectrum, this particular collection of radiations of different wavelengths, this is something which corresponds to emission spectrum. Right? Perfect. This is something which corresponds to emission spectrum. And my dear students, first absorption happened, right? Electrons got excited, then the excited electron came back. It emitted radiation. First absorption took place, then emission took place. That is the reason why you call absorption and emission spectrum as, photonegative of each other. You call them as photonegative of each other. I hope this particular scenario till here is clear to you. Let me know in the chats quickly. People. Every one of you. Absolutely. JEE students can also watch it. No issues. I hope you got the clear-cut idea of the absorption and emission spectrum, right? Which you would have come across many a times. Okay? Perfect, people. Say yes or no in the chats quickly. Everyone. So in absorption spectrum, you get dark lines on the colored background. In emission spectrum, you get colored lines on the dark background. Now, this emission spectrum, we are further going to classify into two types. One is called as continuous spectrum. In case of continuous spectrum, you cannot differentiate the colors on the photographic plate like your rainbow. Like your rainbow. Can you differentiate all the 7 colors in the rainbow? No, you cannot differentiate. The colors are merged into each other. Let's say there's a photographic plate. The colors are merged into each other, right? You cannot differentiate the colors over here. Whenever you see this kind of the spectrum, whenever you see such kind of the emission spectrum, in which you cannot differentiate the colors, you call this particular spectrum as the continuous spectrum. You call this particular spectrum as the continuous spectrum. Second is discontinuous. In the discontinuous spectrum, the colors can be differentiated, right? That means on the photographic plate, in case of discontinuous spectrum, you can differentiate different colors. But in case of continuous spectrum, on the photographic plate, you cannot differentiate the different colors. They'll be merged into each other, right? Now, this discontinuous spectrum, it is further of two types. One is band spectra, one is the line spectra. In case of band spectra, what do you observe? You get a band of colors. For example, this is a red band from here to here. Let's assume. Let's say this is the red band from here to here. Let's say this is green band from here to here. You get band of colors in case of the band spectra. In case of line spectra, you get discrete lines. You get discrete colors over here. You get discrete colors over here on the photographic plate. Perfect. I believe all these things are absolutely clear to you. Now, people, if this general definition of spectra is clear to you, let's try to understand the actual stuff from which the questions are asked. And what do we call that as? We call that as hydrogen spectrum. But before that, do remember these two particular points. They can be asked. Do remember these. Yes, I'll be covering GOC as well. Just wait for that. Do remember, my dear students, band spectrum is formed by the molecules. Molecules are going to form the band spectrum. And line spectrum, it is formed by the atoms. And when it comes to your hydrogen, hydrogen shows emission, discontinuous, and line spectrum. Do remember these. They can be also asked, right? Now, we are going to move into our actual topic. What is our actual topic basically? That is your hydrogen spectrum. Okay? That's your hydrogen spectrum. I want you guys to read these 3 lines over here. Let's see what they exactly say. The electron in the hydrogen atom, when gets excited to the higher energy levels, stays there for 10 raised power minus 8 seconds, falls back to the ground state, right? During which it emits radiation of different wavelengths, which are obtained as colored lines in the spectrum. Now, what it exactly means? Let's try to understand this a bit more in detailed format. Try to understand, people, what I'm going to say, because this is something which is very, very, very important. So first of all, I'm going to make you explain the hydrogen spectrum. From this hydrogen spectrum, a lot of questions are asked. A lot of different types of questions are asked, and you need to understand this properly. Have a look now. Let's say this is N is equal to 1 of hydrogen. Let's say this is N is equal to 1. This is the ground state of hydrogen. N is equal to 1, ground state of hydrogen. Let's assume over here, this is N is equal to 2 of hydrogen. Let's assume this is N is equal to 2 of hydrogen. Okay? Let's assume here you have got N is equal to 3 for hydrogen. N is equal to 3 for hydrogen. Similarly, my dear students, let's say this is N is equal to 4. This is N is equal to 4 for the hydrogen atom. Similarly, let's say you have got N is equal to 5. Let's say this is N is equal to 5 for hydrogen atom. N is equal to 5. Similarly, let's say this is N is equal to 6. Let's say this N is equal to 6 for hydrogen. N is equal to 6. And my dear students, as you all must be knowing, somewhere will be N is equal to infinity. Somewhere here, it's going to be N is equal to infinity. Perfect. Now try to understand what I'm going to say. N is equal to 1 is called as ground state of hydrogen. Ground state. N is equal to 2 is something which you call as first excited state of hydrogen. N is equal to 3 is called as second excited state of hydrogen. This will be third excited state of hydrogen, fourth excited state, fifth excited state, etc. Right? Now, people, If I particularly talk about hydrogen atom, in the hydrogen atom, there is one electron. There is one electron. Let's assume that one electron was here. Assume that one electron was here. For example, this electron, it absorbs some energy. Let's assume that this electron, which is there in the n is equal to 1 of hydrogen, assume that it absorbs some energy. And you know, when electron absorbs energy, it goes into higher energy states. But in the higher energy states, electron is considered to be very less stable, right? It just resides there for 10 raised power minus 8 seconds. And my dear students, when the electron goes from low energy state to higher energy state, in higher energy states, it only resides for 10 raised power minus 8 seconds. Then the electron again jumps back. It again jumps back. And you know, when electron makes a transition from higher energy state to lower energy state, it is going to emit energy in the form of radiation. It is going to emit energy in the form of radiation. That radiation will be having a particular wavelength, right? That radiation will be having a particular wavelength. Now, my dear students, do remember one simple thing. Do remember, when the electron makes a transition, from higher energy state, from higher energy states to shell number 1. When the electron makes a transition from higher energy states to shell number 1. When the electron makes a transition from higher energy states to shell number 1, we get a series of radiations over here. And this particular series of radiations which we get when electron makes a transition from higher to lower, this particular series of radiation you call as the Lyman series. And my dear students, let me tell you, whatever radiations we get in Lyman series, these radiations, they fall into ultraviolet region. Anyways, I'm going to talk about that more in detail in some time. So from now onwards, whenever I'll be talking about the Lyman series, in Lyman series, what do we get? We get a series of radiations when the electron makes a transition from higher energy states to shell number 1, right? Perfect. So if I ask you, what is the ground state in case of Lyman series? In case of Lyman series, your ground state, which is represented by N1, your ground state is 1, right? And your higher energy states, which I'm representing with N2, it can be 2, it can be 3, it can be 4, it can be infinity. Perfect. So this series of lines we got over here, that's your Lyman series, number 1. Number 2, when the electron makes a transition from higher energy state to shell number 2, when the electron makes a transition from higher energy states to shell number 2, again we get series of radiations. And those series of radiations which we got when the electron makes a transition from higher energy state to shell number 2, you call this series of radiations as the Balmer series. In case of Balmer series, your ground state, in case of Balmer series, the electron finally reached back to shell number 2. So the lower energy state in case of Balmer series is 2, and the higher energy state in the Balmer series, it can be 3, it can be 4, it can be 5, right? Similarly, when the electron makes a transition from higher energy state to shell number 3, you get a series of radiations over here, right? Perfect. This particular series you call as Lyman-Balmer. This is what you call as Paschen series. And in case of Paschen series, the lower energy state is 3 and your higher energy state, it is 4, 5, it can be 6, it can be infinite, etc., etc. Okay. Let me tell you one more thing. As I told you in the beginning, whatever radiations we got in Lyman series, they fall in ultraviolet region. In case of Balmer series, whatever radiations we'll be getting, they'll fall into visible region. That means when these radiations fall on the photographic plate, you can see them. They fall into visible spectrum. You can see them, right? You can see them with your eyes. Ultraviolet we cannot see, right? Visible we can see. Perfect, right? And whatever series of lines, whatever series of radiations we got in Paschen, right? They fall in, this is ultraviolet, UV, this is infrared. They fall in infrared region. Similarly, there are few more series of lines which you have to remember. What are those? When the electron makes a transition from higher energy state to shell number 4, where you get a series of lines, you call them as, this was Lyman, Balmer, Paschen, This is called as bracket. This is something which you call as bracket series, in which the lower energy state is 4 and the higher energy state can be 5, it can be 6, it can be 7, etc., etc. And at the end, when the electron makes a transition from where to where? From higher energy state to shell number 5. From higher energy state to shell number 5. Okay? You get a series of lines again, which you call as fund series. PFUND. PFUND. Fund series. Right? And in case of fund series, the ground state, the lower energy state in case of fund series is 5. And the higher energy states will be, it can be 6, it can be 7, it can be 8, etc., etc. Similarly, when the electron makes a transition from higher energy state to shell number 6, like this, Again, you get a series of lines, and those series of lines you call as Humphrey series. You call that as Humphrey series. In case of Humphrey series, the lower energy state, which I'm representing the N1, that is 6, and higher energy state can be your 7, it can be 8, right? Till infinity. Perfect. Now, this particular series falls in all the radiations in Lyman series. They fall in ultraviolet. These fall in visible. These fall in infrared, right? Bracket also falls in infrared. Fund also falls in infrared. Humphrey also falls in infrared. Do you remember all these things? Right? What I'm trying to say over here is this particular line. Just a second. Lyman series. In case of Lyman series, the lower energy state is 1. Higher energy state can be 2, 3, 4. And all the radiations which you get over here, when the electron makes a transition from higher to n is equal to 1, all these radiations, they fall in ultraviolet, right? Balmer series radiations, they fall in visible. Paschen series, infrared. Bracket series, infrared. Fund series, you can call this also as infra, or you can say far infrared. Similarly, Humphrey series, you can also call this as far infrared, right? So do remember this particular scenario. Question has been asked once in your NEET examination from this particular table. The question was, in case of Balmer series falls in what? It falls in visible spectrum. This was once asked in your NEET examination. Balmer series falls in visible spectrum. Do remember this particular scenario. Now people, let's analyze this particular diagram more. There are few terminologies which I would want you guys to remember. What are those terminologies? My dear students, if you analyze the Lyman series, this particular line over here, I will be calling this as this particular line over here. I'll be calling it either as H alpha line, or I will be calling it as first line of Lyman series. I'll be calling it as first line of Lyman series, or you can call it as H alpha line. Similarly, this particular line from 2 to 1, this particular line is something which I call as second line of Lyman series, or you can call it as H beta line. Right? Similarly, this particular line over here, in the Lyman series, you will be calling it as third line of Lyman. You'll be calling it as third line, or you'll be calling it as H gamma line. Similarly, fourth line, fifth line, etc., etc. Right? Similarly, my dear students, if you look at the Balmer series, this line you'll be calling as, this particular line, you'll be calling it as first line of Balmer, second line of Balmer, third line of Balmer, fourth line of Balmer, first line of Paschen, second line of Paschen, third line of Paschen, fourth line of Paschen, first line of bracket, second line of bracket, third line of bracket, first line of fund, second line of fund, first line of Humphrey, similarly second line of Humphrey. First line is also called as H alpha line. Second line is also called as H beta line. First line is called as H alpha. Second line is called as H beta. Perfect. I hope till here every single thing is clear. Now, my dear students, there are some very important things which we have to discuss now. See, understand it like this. If I talk about Lyman series, electron can make a transition from 2 to 1. It can make a transition from 3 to 1, 4 to 1, 5 to 1. And you know, when the electron makes the transition from higher energy state to lower energy state, it emits energy in the form of radiation. That radiation will be having some frequency. That radiation will be having some wavelength, right? How do we calculate the wavelength, the frequency, the wave number of the radiation which is emitted or absorbed during the transition of the electrons? How do we do that? That's important, guys. For that purpose, what I'll be doing, I'll be introducing a result. I'll be introducing a formula which is called as the Rydberg's formula. I'm going to introduce a result over here. I'm going to introduce a formula over here, that is the Rydberg's formula. I'm not going to derive it. I'll just give this formula and show how it's to be applied in the questions. This Rydberg's formula, why it's used? Why am I going to give you this result? I'll say this formula is used to calculate wavelength, frequency, wave number of what? Of the radiation emitted by the electron when it makes a transition from higher energy state to lower energy state, or absorbed by the electron when it makes a transition from lower to higher, right? So for that particular purpose, I'm going to introduce the Rydberg formula. And Rydberg's formula says that your wave number, what is wave number? That is inverse of your wavelength, is equal to, this is R, Rydberg's constant, Z square. Z represents your atomic number of the atom, right? 1 upon N1 square minus 1 upon N2 square. Now you must be thinking what this N1 and N2 is all about. Let me tell you, N1, be careful with this. N1 always represents your lower energy state, and N2, it always represents your higher energy state. Always represents your higher energy state. And my dear students, for calculation purpose, do remember 1 divided by Rydberg's constant, 1 by R value for calculation purpose will be always taken as 911.5 angstroms. Just to reduce the calculations, you are going to take the value of 1 by R as 911.5 angstroms. Right? Right, people? Now try to understand why I gave you this particular formula. In order to get the wavelength, in order to get the frequency, in order to get the wave number of the radiation which is emitted or absorbed during the transition, either from higher to lower or from lower to higher, right? Now people, let's have a look exactly how this particular result is used. Let's first of all try to analyze your Lyman series. Let's try to analyze your Lyman series. In case of Lyman series, you already know electron makes a transition from a higher energy state to shell number 1. Now, my dear students, the first point in Lyman series, if I talk about the first line of Lyman, which is also called as H alpha line, just tell me one thing. In case of first line of Lyman, the transition will be from where to where? Just tell me that. First line of Lyman means the transition will be from 2 to 1. The transition will be from 2 to 1, right? Electron will move from 2 to 1 in the first line of Lyman. Now, which one is lower energy state? 1. I should be calling this as N1. Which one is higher energy state? 2. I should be calling this as N2. Now, we know when the electron makes a transition from higher to lower, it emits energy in the form of radiation. That radiation has got some wavelength. Let's calculate the wavelength of the radiation which is emitted. So I'll be using the Rydberg's formula. 1 divided by lambda is equal to R Z square. I'm talking about hydrogen. Z is 1. 1 upon N1 square minus 1 upon N2 square. This is 1 divided by lambda is equal to R. This is going to be 4 minus 1, 3. 3 divided by 4 exactly, right? Or you can take the reciprocal. So lambda is going to be 4 divided by 3 multiplied by 1 by R. And you all must be knowing 1 by R is nothing. That is 911.5, right? And this is going to be the wavelength of the radiation emitted during the first line in angstroms. Is it clear? Is it clear, people? I believe it's clear, right? I believe it's clear. If I talk about the second line of Lyman, you should be able to solve it again. If I talk about the second line of Lyman, okay, second line of Lyman. In second line of Lyman, what exactly happens? In second line of Lyman series, the electron makes a transition from 3 to 1. Now, this is the lower energy state, N1. This is the higher energy state, N2. When the electron makes a transition from 3 to 1, again, it's going to emit radiation, which will be having some wavelength. Let's calculate the wavelength. 1 by lambda is equal to R. Z square, Z is 1. 1 upon n1 square minus 1 upon n2 square. So this is going to be simply 1 divided by lambda is equal to r, and it's going to be 8 divided by 9, right? Take the reciprocal. So lambda has to be 9 divided by 8 multiplied by 1 by r. And my dear students, this is 9 by 8. 1 by r value is 911.5 angstroms, right? Just solve it, get the answer exactly in angstroms, right? I believe it's clear. I believe it's clear. There is one more term here. There is one more term here. What is that term? My dear students, in Lyman series only, I'm going to introduce one more term. That's called as series limit. That's called as series limit in Lyman series. Series limit in Lyman. Series limit is also called as shortest wavelength. It is also called as shortest wavelength. Sometimes they'll ask you directly, calculate the shortest wavelength in Lyman. Sometimes they'll ask you, calculate the series limit in Lyman. Both the things are same. Now, series limit or shortest wavelength in Lyman. First of all, you must be knowing now your delta E. Delta E is the energy gap between two shells, right? Energy gap between two shells. That is inversely proportional to lambda basically. Delta E is equal to hc by lambda, right? Delta E is equal to hc divided by lambda. Now your energy gap and lambda, they are directly or inversely proportional. What do I have to calculate? I have to calculate the shortest wavelength. I have to calculate the shortest wavelength. For the wavelength to be shortest, energy gap between the shells should be maximum. For lambda to be minimum, for lambda to be shortest, delta E, it has to be maximum. Now tell me, you tell me, in the Lyman series, what is the maximum energy gap? Should I take the transition from 2 to 1, 3 to 1, 4 to 1, 5 to 1, or infinity to 1? Tell me that. So in case of the series limit in Lyman series, I will have to take the transition from infinity to 1. Then only the energy gap will be maximum. And when the energy gap is maximum, that means your wavelength emitted will be minimum. That minimum wavelength, shortest wavelength, is what you call a series limit. As simple as that, right? Now, this is your lower energy state. This is your higher energy state. And you know when the electron makes a transition from higher to lower, it's going to emit radiation, which has got some wavelength. So 1 divided by lambda is equal to r. Z is 1 for hydrogen, 1 upon n1 square minus 1 upon n2 square, right? So it's going to be 1 divided by r is equal, 1 divided by lambda is equal to r. 1 by infinity is 0 basically, right? So take the reciprocal, lambda will be 1 divided by r. 1 by r, you already know that's 911.5 angstroms. So this is the minimum wavelength which will be emitted in case of Lyman series, right? This is the minimum wavelength. This wavelength in case of Lyman series is also called as series limit of Lyman. Series limit of Lyman, right? I believe you can easily solve all these things from now onwards. Yes? Similarly, guys, let's say you have got the Balmer series. Can you calculate all these things for the Balmer series again? You should be able to. Can't you calculate all these things for the Balmer series again? My dear students, you should be able to. First, what is that? I'm talking about H alpha line of Balmer. H alpha line means first line of Balmer. H alpha line means first line of Balmer. First line of Balmer, right? First line of Balmer. In case of Balmer series, electron makes a transition from higher energy states to shell number 2, right? Now, I'm asking about first line of Balmer. First line of Balmer means the electron is making a transition from 3 to 2. This is the lower energy state. This is the higher energy state, right? So the electron is making a transition from 3 to 2. It's going to emit radiation, which will be having some wavelength. So 1 by lambda is equal to r. Z square, that's 1 square. 1 upon n1 square, 2 ka square is 4, minus 3 ka square is 9. So 1 divided by lambda is equal to r. 9 minus 4 is 5, divided by 36. Take the reciprocal, lambda is equal to 36 divided by 5, multiplied by 1 by r, that's 911.5. And this value is going to be in angstroms. Done and dusted? Done and dusted? Now, if I ask you about the series limit, in Balmer, or I'll be calling this as shortest wavelength, lambda minimum. right? I'll be calling it as lambda minimum. This was your lambda minimum, by the way, right? This was your lambda minimum. This was your lambda minimum in Lyman. Now, lambda minimum in Balmer. For the wavelength to be minimum, energy gap has to be maximum. In Balmer series, when do you see the maximum? In which transition you see the maximum energy gap? In which transition you see the maximum energy gap? In Balmer, it's going to be again infinity to 2. This is your N1 value. This is your N2 value. Now 1 divided by lambda minimum in Balmer is going to be R. Z square is 1. 1 upon N1 square minus 1 upon infinity ka square, right? So 1 divided by lambda minimum is equal to R, and it's just going to be 1 by 4 because 1 by infinity is 0. So lambda minimum in case of Balmer is going to be 4 multiplied by 1 by R, that is 911.5, and the answer is going to be angstroms. So this is the series limit in case of Balmer series. This is the series limit of the Balmer. This is the series limit of the Balmer, right? This is the series limit of the Balmer. I believe it's clear. I believe it's clear. Right, people? I believe it's clear. Okay, tell me one more thing. If I talk about Lyman series again, since I told you in case of Lyman series, I showed you how to calculate lambda minimum. How to calculate lambda minimum. If I ask you, calculate lambda maximum in Lyman series. Lambda maximum in Lyman series. Calculate lambda maximum in Lyman series. For lambda to be maximum, delta E has to be minimum. Delta E has to be minimum. For lambda to be maximum, delta E has to be minimum. Now in Lyman series, delta E has to be minimum. Delta E has to be minimum. Look at the Lyman series. Look at the Lyman series. Where do you see the delta E minimum? Delta E minimum in Lyman series is from, the transition is from 2 to 1. So transition from 2 to 1 basically. I have to consider transition from 2 to 1. And here I have considered the transition from 2 to 1. So should I be calling this wavelength as minimum or maximum? This wavelength is going to be the maximum wavelength, right? It's going to be the maximum wavelength. It's going to be the maximum wavelength, lambda maximum in Lyman, right? Similarly, if I ask you lambda maximum in Balmer, just tell me the transition. Lambda maximum in Balmer. Energy gap has to be minimum in Balmer. When is the energy gap minimum in Balmer? When the electron makes a transition from 3 to 2. And that 3 to 2 we have already analyzed here. So this is lambda maximum in Balmer. Right? This is lambda maximum in Balmer. Perfect. Clear, guys? So I hope these sort of questions you can easily solve from now onwards. Perfect. Look at the first question. Can you solve this? Can you solve this question? Calculate the wavelength of H alpha line of Balmer series. We have done this question. We have calculated this wavelength. Series limit in Lyman series. We have solved this question. We have solved this question too. The third one, H beta line of Paustian. H beta line of Paustian. Lyman, Balmer, Paustian. So N1 has to be 3, right? First line will be 4 to 3. First line will be 4 to 3. Second line will be 5 to 3. Second line is called as H beta line. H beta line. So the transition has to be from 5 to 3. Now we can use the formula, get the answer, 1 by lambda, right? Perfect. So these sort of questions you should be able to solve easily from now on. Look at this one. Look at this particular question. Look at this particular question. What transition in hydrogen spectrum would have the same wavelength as the Balmer transition? N is equal to 4 to N is equal to 2 of He positive spectrum. What exactly it means? Try to understand. For example, this is the hydrogen atom. This is your He positive ion. One is hydrogen, one is He positive. Perfect. In case of He positive, you know the atomic number. First of all, hydrogen atomic number is 1, right? And helium atomic number, you already know, that's 2. Perfect. In case of helium, the electron makes a transition from 4 to 2. The electron makes a transition from 4 to 2. Perfect. When the electron will be making a transition from 4 to 2, it's going to emit some wavelength. Right? Which I call as lambda over here. Perfect. Now, as per the question, what should be the transition in case of hydrogen? What should be the transition in case of hydrogen? Such that the electron is going to emit the same wavelength as was emitted by He positive. That's the question. Perfect. What I'll be doing exactly? I'll be using Rydberg's formula for this hydrogen as well as for this one, for this He positive. It's going to be 1 divided by lambda is equal to R Z square 1 square 1 upon N1 square minus 1 upon N2 square. Now, my dear students, I'm calling this is equation number 1. I'm calling this equation number 1. Use the Rydberg's formula for this particular transition as well. So it's 1 divided by lambda is equal to R Z square. So 2 ka square is 4. 1 upon N1 square minus 1 upon N2 square. So this you can write like this. 1 by lambda is equal to R, right? This is going to be 4 cancel. So 1 by 1, or you can write 1 by 1 ka square minus 4. This 4 ones are 4 4s are. So this is 1 by 4, which can be written as 1 by 2 ka square. My dear students, if you compare both these two equations, what you will analyze here? Compare both these equations. What you are going to understand? See, lambda emitted here as well as lambda emitted here. That should be the same. So LHS side in both the equations is same. If LHS side in both the equations is same, that means RHS side in both the equations should be same too, right? So on comparing these two equations, look at this N1. So you got to know your N1 is basically 1 in hydrogen and your N2 over here, N2 has to be 2. So in case of hydrogen atom, the transition should be from 2 to 1. Then the electron is going to emit the same wavelength as was emitted by He positive when the electron made a transition from 4 to 2. I believe it's clear to everyone. Yes? Say yes or no in the chats. Say yes or no in the chats quickly. Calculation of maximum spectral lines. Calculation of maximum spectral lines when the electron makes a transition. Calculation of maximum spectral lines. And this particular result which I'm going to give you, it's for large number of atoms. Try to understand what exactly I'm going to talk about. For example, guys, just to make you understand, let's say this n is equal to 1. Let's say this n is equal to 2. Let's say this n is equal to 3, right? This n is equal to 3. For example, the electron is present in n is equal to 3. And it has to come to 1 exactly. So the transition, for example, is from 3 to 1. The electron has to come from 3 to 1. If I ask you how many possible ways are there by means of which electron can come from 3 to 1. See, first way, electron can directly come from 3 to 1, right? So the transition can be 3 to 1 directly. And when the electron makes a transition from 3 to 1, it's going to emit a radiation, right? That radiation I'm represented by a line, by spectral line. Perfect. Are there other ways too? Yes, there are other ways too. Electron will first come from 3 to 2. When the electron comes from 3 to 2, one spectral line emitted. Then from 2 to 1, one more spectral line emitted. So how many total spectral lines are emitted when the electron makes a transition from 3 to 1? How many total spectral lines emitted when the electron makes a transition from 3 to 1? 3 spectral lines in total are emitted. Right? But you're not going to use this approach always. Like one by one, you will check all the possibilities. I'll directly give you one result which you are going to remember from now on, people. What is that result? Have a look. Calculation of maximum spectral lines. It is N2 minus N1. N2 minus N1 multiplied by N2 minus N1 plus 1 divided by 2. This is how you are going to calculate the maximum spectral lines emitted when the electron makes a transition from higher energy state to lower energy state. For example, imagine that the electron is making a transition from 6 to 1. So this is your higher energy state N2. This is your lower energy state N1. So if I ask you how many spectral lines, number of spectral lines emitted right now, number of spectral lines observed right now is equal to N2 minus N1. 6 minus 1, that's 5. N2 minus N1, that's 5. N2 minus N1, that's 5. 5 plus 1, 6 divided by 2. So how many? 15 maximum spectral lines will be observed. You'll observe 15 maximum spectral lines. Now, my dear students, if I ask you, out of these 15 spectral lines, out of these 15 radiations which are emitted, how many spectral lines will fall in Lyman? How many spectral lines will fall in Balmer? How many spectral lines will fall in Paschen? Right? If I ask you something like that, do remember number of spectral lines. Number of spectral lines falling into a particular region, falling into a particular series, I'll say, falling into a particular series is always equal to higher energy state minus ground state of that particular series which you are talking about. What does that mean? Electron right now is making a transition from 6 to 1. So how many spectral lines are observed? 15. 15 spectral lines are emitted. 15 radiations are emitted, which have got different wavelengths, right? Out of these 15 radiations, how many radiations will fall in Lyman if I ask you? How many radiations will fall into Lyman? What you'll say? Number of spectral lines which fall into Lyman category. It has to be equal. It has to be equal to N2. That is the higher energy state, which right now is 6, minus ground state of Lyman. Ground state of Lyman is 1. So out of 15 spectral lines, there'll be 5 spectral lines which will fall into the category of Lyman. Similarly, how many will fall into the category of Balmer? Higher energy state minus ground state of Balmer is 2, right? How many spectral lines out of the 15 spectral lines? How many will fall into Paschen? Higher energy state minus ground state of Paschen, 3, right? Lyman, Balmer, Paschen. Then comes your bracket. Then comes your bracket. It's going to be higher energy state minus ground state of bracket. That's 4. That's 2. Similarly, fund. Fund will be 1. There'll be 1 spectral line which you'll observe in the fund series as well. Now, if you add them up, 5 plus 4 plus 3 plus 2 plus 1, 5, 4, 9, 9, 3, 12, 12, 2, 14, 14 plus 1, 15. So in total, how many spectral lines are observed? In total, 15 spectral lines are observed, out of which 5 will fall in Lyman, 4 will fall in Balmer, 3 will fall in Paschen, 2 will fall in bracket, and 1 will fall into the fund. Right, people? This particular question can be asked too. Do remember. Do remember, people. Do remember. Do remember. Look at this particular question. Try to solve this. Try to solve this. Hydrogen atom in ground state is excited by monochromatic radiation of wavelength lambda. Right? Hydrogen atom in ground state. Hydrogen atom is in ground state. Okay. See, this is the ground state of hydrogen. This is the ground state of hydrogen. Hydrogen is present in the ground state. It is excited by a monochromatic light. A monochromatic light is falling on this electron, right? Whose wavelength is lambda. Perfect. When this monochromatic light falls on this electron, the electron excites. It goes to higher energy state. It goes to N2. The electron reaches N2, for example. Electron reaches N2. Perfect. On coming back to the ground state. Now, since you know when the electron makes a transition to higher energy state, at higher energy state, electron is very unstable. So it jumps back. Now the electron is jumping back. And when the electron is jumping back, how many different spectral lines are observed? 15 spectral lines are observed. Calculate lambda. We have to calculate this lambda, which was absorbed by the electron. How exactly you're going to do it? See guys, maximum number of spectral lines obtained are 15, right? These are the maximum spectral lines obtained. Perfect. Maximum spectral lines obtained, 15. Now, people, maximum spectral lines obtained is N2 minus N1. N1 is 1. N2 minus N1. This is N2 minus N1. This is N2 minus N1 plus 1 divided by 2. Correct? So this one got cancelled. 15 to 30. So 30 is equal to N2 ka square minus N2. So you are getting a quadratic here. N2 square minus N2 minus 30 is equal to 0. You got a quadratic equation. You got one quadratic equation. I hope all of you know how to solve a quadratic equation. I hope you know that, right? So when you solve this quadratic equation, you'll be getting two values of N2. One you'll be getting 6, one you'll be getting minus 5. Minus 5 cannot be the value. It has to be 6. That means the electron has gone from 1 to 6. The electron has gone from 1 to 6. And now the electron is coming back from 6 to 1. Now the electron is coming back from 6 to 1. What we have to calculate? We have to calculate the wavelength. Whatever wavelength electron had absorbed in the beginning, so that it could go from 1 to 6. When it jumps back from 6 to 1, it's going to emit the same wavelength. It is going to emit the same wavelength, right? So I'm going to assume that the transition is from 6 to 1. Perfect. The transition is from 6 to 1. So calculate the wavelength emitted. 1 by lambda is equal to R. Hydrogen, Z is 1. 1 upon N1 square minus 1 upon N2 square. Perfect. So 1 divided by lambda is equal to R. This is going to be 35 divided by 36. So take the reciprocal. So lambda emitted is equal to 36 divided by 35 multiplied by 1 by R is 911.5, and the answer is going to be angstroms. So this much wavelength is emitted by the electron when it makes a transition from 6 to 1. That means same wavelength it would have absorbed too when it would have made the transition from 1 to 6. Simple? Simple, people? Right? I believe this sort of a question you can easily solve from now on. Okay, look at this. What this question says. Electron in the hydrogen atom jumps from some higher level up to third energy level. Electron jumps from higher level to third energy level. The electron jumps from higher level to third energy level, right? How many spectral lines are observed? If 6 spectral lines are possible for the transition, find the initial position of electron. See, electron is right now at N2. Perfect. It is the initial position. Now the electron has to jump to 3. How many spectral lines? How many spectral lines are possible? 6. Find the initial position. We have to get the value of N2. It's again simple. So how many maximum spectral lines? 6 is equal to N2 minus N1. This is N2 minus N1 plus 1 divided by 2. Solve this equation, get the value of N2. That was the initial position of the electron. You can easily solve it. Nothing to look at this. Okay, look at this particular question. In hydrogen atom, electron makes a transition. Okay, from where to where? From 4th excited state. Guys, be careful with the terminologies. From 4th excited state. 4th excited state is n is equal to 5. Up to second state. So the transition is from 5 to 2. Okay, the transition is from 5 to 2. So this is your N1 and this is your N2. Then 10 different spectral lines are observed. 6 different number of lines belonging to Balmer, number of lines belonging to Paschen. Okay. So first of all, let's calculate the total number of spectral lines. Total number of spectral lines will be equal to N2 minus N1. This is going to be N2 minus N1 plus 1 divided by 2. This value is going to be 3. This value is going to be 3 plus 1, 4 divided by 2. 4, 3, 12 divided by 2, 6. So in total, 6 spectral lines. 6 different spectral lines are observed, right? Now, out of 6, how many will fall into Balmer? Balmer. So number of spectral lines which will fall into Balmer. How do we calculate that? It's equal to higher energy state minus ground state of Balmer. What is the higher energy state? Higher energy state here is 5 minus ground state of Balmer, Lyman-Balmer, it's 2. So 5 minus 2 is 3. So 3 spectral lines will belong to Balmer. Similarly, how many spectral lines will belong to Paschen? Higher energy state minus ground state of Paschen, Lyman-Balmer Paschen. So 5 minus 3, 2. Number of lines belonging to Paschen, that's 2. So B, C as well as D. That's correct. That is correct. Let me know once in the chats if all the things are clear till here. Quickly, guys. Quickly, people. Again, one simple question. I believe you can easily solve this question, right? Correct? From spectrum, this is your homework question, right? And you are going to let me know its answer in the comment section of the video at the end, in the comment section. Perfect, guys. Is it clear? All the things are clear till here? So this was your detailed hydrogen spectrum. I believe if any question is asked from hydrogen spectrum, you should be able to solve that question on your own. You should be able to solve that question. Will you be? Can you solve the question? Are you sure about that? Guys, say yes or no in the chats quickly. We don't have much of a time here. Quickly, everyone. Zainab, you just increase your settings. I think there is something wrong in your settings of this video. Say quickly in the chats if it is clear to everyone, guys. GOC will be also done. I've told you. Next week, Monday, you'll have GOC session. I'm asking, is it clear to everyone? Everything is sorted? Say yes or no in the chats quickly. I think you don't want to continue with this session, yeah? Should I end the stream then? I think you've studied atomic structure. So there is one topic, this is one more important topic, that is de Broglie's hypothesis. Let's exactly get to know what this de Broglie's hypothesis is all about. Let's exactly get to know what this de Broglie's hypothesis exactly is all about. My dear students, this de Broglie's hypothesis, what does it explain first of all? It explains the dual nature of matter. It explains the dual nature of matter. See, first of all, if I talk about light, you already know light has got duality. Light has got duality. Light has got dual nature. What is meant by that? What is meant by that? See, just to make you understand, if you know light, it shows certain phenomenon. It shows certain phenomenon. For example, reflection, for example, refraction, for example, diffraction. There are many phenomena shown by the light. There are many phenomena shown by the light. Now, some of the phenomena of light are explained by considering light to have particle nature, and some of the phenomena of the light are explained by considering light to have the wave nature. So there are many phenomena shown by light, out of which some of the phenomena are explained by considering the light to have wave nature, and some of the phenomena are explained by considering light to have the particle nature, right? So in short, I can say light has got duality basically, right? Light has got dual nature, particle nature as well as wave nature, particle nature as well as wave nature, right? What Heisenberg said? Heisenberg said it is not only about the light. Whatever exists in the universe, every single thing shows the duality. Whatever matter we have, be it electron, be it proton, be it photon, whatever matter we have around us, every single thing has got the duality. Every single thing shows particle nature as well as wave nature. This is the hypothesis as per de Broglie is concerned. This is the hypothesis as per de Broglie is concerned. De Broglie said whatever matter is there in the universe, every single thing, be it electron, be it proton, be it photon also, right? Every single thing has got duality. Every single thing has got particle nature as well as wave nature, right? Let me make it a little more simple for you. What de Broglie exactly said? Let's say this is the particle. This is the object, for example. This is a small object whose mass is m. Let's assume that this small object is moving with velocity v. This small object is moving with velocity v. If this object has mass m, velocity v, so this object carries some momentum p, which is equal to m into v. This object, it carries linear momentum, right? It carries linear momentum. Perfect. Now, my dear students, what this de Broglie said, whenever you have got an object having certain mass moving with certain velocity, right? Moving with certain velocity, apart from its particle nature, there will be a wave associated with this particular object. There will be a wave associated with this particular object. And the wave which is associated with the object, you either call it as a matter wave, or you call it simply as de Broglie's wave. You simply call it as de Broglie's wave. For example, this is the marker, for example, right? This marker has got some mass, it has got some velocity. This marker has got some mass. It is moving with some velocity. It's moving with some velocity, right? So it has got mass, it has got velocity, it has got linear momentum. Linear momentum is the characteristic of a particle. Linear momentum is the characteristic of a particle, right? Now, as per de Broglie, if this marker is moving, with the marker, there will be a wave associated with it. And that wave is something which he called as de Broglie's wave. That wave is something which he called as de Broglie's wave. Perfect. That wave is something which he called as de Broglie's wave. Right? That wave is something which he called as de Broglie's wave. Now, the point is very simple. If there is a wave associated with every particle, that means this wave will have got certain wavelength, and that wavelength associated with the de Broglie's wave, that is represented by lambda. And as per de Broglie's concerned, wavelength of the de Broglie's wave, which is associated with the object moving with some velocity, it is inversely proportional to the linear momentum carried by the object. It is inversely proportional to the linear momentum carried with the object, right? It is inversely proportional to the linear momentum carried with the object. What is lambda here? This is something which you call as de Broglie's wavelength. This is something which you call as de Broglie's wavelength, right? De Broglie's wavelength of the de Broglie's wave, which is associated with the particle which is moving with some velocity v. What is p? P is something which we call as linear momentum. P represents linear momentum of the object which was moving, right? So he related both the things. This lambda, it is the characteristic of wave. This linear momentum, it is the characteristic of particle. So he related both the things. He related both the things for the object, right? He told your de Broglie's wavelength, that's inversely proportional to the linear momentum. Now guys, have a look. If I remove the proportionality sign, you're going to get the constant h divided by p. H divided by p. This is one of the equation which you are going to remember from now onwards, right? Similarly, what is p basically? P is the product of mass and velocity. P is the product of mass and velocity. So this one more result to calculate de Broglie's wavelength of an object, right? Perfect. Now, my dear students, let's try to understand one more thing. See, if I talk about this particular object, right? It has got mass, it has got velocity. Perfect, it's moving. There is a de Broglie's wave associated with it. Okay. One more thing. If it has got mass, if it has got velocity, it will be having some kinetic energy as well. And kinetic energy of that particular object is simply half of mv square, right? Half of mv square. If I just do one thing, if I multiply and divide with mass, so this becomes m square in the numerator, in the denominator it will be m. So can I say kinetic energy is equal? This is m multiplied by v ka whole square divided by 2m. Perfect. So it's going to be 2m multiplied by kinetic energy is equal to m multiplied by v is momentum. So this is p ka square. So p from here comes out to be under root of 2m multiplied by kinetic energy, right? So in this particular expression, you can say lambda is equal to h upon under root of 2m multiplied by kinetic energy associated with the object which is moving with velocity v. So this is one more result to calculate de Broglie's wavelength in terms of kinetic energy, right? de Broglie's wavelength in terms of momentum, de Broglie's wavelength in terms of kinetic energy. Are there some other results too to calculate de Broglie's wavelength? One more thing, guys, which I forgot to tell you. This de Broglie's wavelength, de Broglie's hypothesis. If I particularly talk about de Broglie's hypothesis, it gives satisfactory results for your microscopic particles. What does that mean? See, I am the macroscopic object, right? I'm the macroscopic object. I've got some mass. I'm moving with certain velocity. I've got some mass. I'm moving with certain velocity. Definitely, there will be a wave associated with me, but the wavelength of that wave will be negligible. That will be negligible. That's why this particular concept, we relate this particular concept normally with the microscopic particles, right? We relate it with the microscopic particles particularly. Okay, why is that? The reason is pretty much simple. I am the macroscopic object. I have got some mass. I'm moving with some certain velocity v. That means there will be a de Broglie's wave associated with me. Absolutely. But the wavelength of that particular wave will be negligible. So you're not going to consider it. Right? Perfect. All right. So till now, what did we calculate? We calculated the de Broglie's wavelength in terms of momentum. We calculated the de Broglie's wavelength in terms of kinetic energy. Now, is there any other result by means of which we can calculate de Broglie's wavelength? Absolutely, there is one more result. Let's have a look exactly what that result is. My dear students, try to understand one simple thing. Imagine that you have got a charged particle. If a charged particle is accelerated, at a potential difference of V volts, as per your work energy theorem, change in the kinetic energy will be equal to work done by the battery, I'll say, by the source, I'll say. What does it mean exactly? Try to understand what it exactly means. For example, guys, this is a plate. This is one more plate. I'm connecting these two plates with an external battery. Right? With an external battery. Perfect. This plate is connected with the positive terminal, so it carries the positive. This carries the negative. Perfect. Now imagine I've got a charged particle Q. I've got a charged particle over here. Right? I've got a charged particle whose charge is plus Q. Right? Let's assume the battery is turned on right now. Let's assume that the battery is not connected right now. If the battery is not connected, there are no charges on these plates, and this charged particle is at rest. This charged particle, imagine the battery is not connected right now. The charged particle is at rest, so its initial kinetic energy will be zero. Now, when you turn the battery on, this negatively charged plate is going to attract this positively charged towards itself, right? Initially, the kinetic energy of the particle was the charged particle was zero. Now, since when you turn the battery on, this battery, the negative plate of the battery, it started attracting it towards itself, due to which it attains the kinetic energy, right? Now, as per your work energy theorem, change in the kinetic energy of the particle is equal to the work done by the battery. Let's assume the voltage of the battery was V. Change in the kinetic energy is going to be final kinetic energy. Minus initial. Initial is zero. Is equal to work done by the source. Which is equal to charge multiplied by potential difference. So, if a charged particle is accelerated under certain potential difference, do remember, change in kinetic energy as per work energy theorem has to be equal to maximum work done. So, Ke is equal to Q multiplied by V. That means we are going to get one more result. And the result is lambda, de Broglie's wavelength is equal to h upon, it was under root of 2m multiplied by kinetic energy. Instead of that, you'll write charge on the particle multiplied by voltage at which it is being accelerated. Guys, it's simple. If you'll be having a charged particle, if it's accelerated, if the charged particle is moving, definitely there'll be a wave associated with it. That wave will be having certain wavelength. How do we calculate that wavelength? Like this, right? Particularly if I talk about electron. For electron, if the electron is accelerated at some potential difference, at that point, de Broglie's wavelength associated with the electron will be equal to h is constant, mass of electron you know, charge on electron you know, right? It will be equal to 12.27 divided by under root of v, where v is the potential difference at which the electron is accelerated, and this value will be in angstroms. This result is particularly for the electron. Similarly, you can calculate for alpha particle, you can calculate for proton, right? But mainly we'll use this particular result here. Okay, I believe it's clear to everyone. Now people, as I told you, this de Broglie's hypothesis, it suggests that whatever matter is around us, everything has got duality, has got wave nature as well as particle nature. When a particle having certain mass moves with certain velocity, that means it has got some momentum. When this particle moves, right, with the particle, there will be a wave associated with it, right? That wave is something which you call a de Broglie's wave, whose wavelength is lambda. He gave the relation between lambda and p. Lambda is inversely proportional to p, right? Lambda is inversely proportional to p. Perfect. Lambda is inversely proportional to p. And we got all the results by means of which we can calculate the de Broglie's wavelength of a de Broglie's wave which is associated with some object, right? Okay. Now guys, the wave nature of the matter, was basically, it was explained by this Davison-Germer experiment. There's the experiment which you'll study in your class 12 physics, I believe, right? Through that particular experiment, it was believed that matter has got wave nature, right? How exactly? Let me show it. Just a glimpse of it. I'm not going to teach this in detail, just for an idea I'll give you. See guys, if you particularly talk about light shows a phenomenon that's called as diffraction. Light shows a phenomenon that's called as diffraction, and diffraction is explained by considering light to have the wave nature. It is explained by considering the light to have the wave nature, right? Now what happens over here in Davison-Germer experiment? My dear students, over here you are going to take a beam of electrons. This beam of electrons you are going to pass through a slit, right? And over here you have kept a photographic plate, for example. When you pass the electron beam through a slit, what you will observe? You will observe these circular patterns. On this photographic plate, right? You'll observe these circular patterns on this photographic plate. This phenomenon is something which you call as diffraction, basically. But this diffraction was shown by light. Basically. And that diffraction shown by light was explained by considering light to have the wave nature, right? But here, did I take a light or electron? I took electron beam. Electron beam also showed diffraction, right? So diffraction shown by electron beam will be also explained by considering this electron to have the wave nature. Yeah? I hope it's clear to everyone. Perfect. That's what I'm telling you over here. The wave nature of the matter was experimentally proven by this particular experiment, which in detailed format you will study in your class 12 physics. Just the idea of things I gave you here. Perfect. I hope you remember all the results which I gave you. See, these are all the things which I told you. This concept is valid particularly for what? Microscopic particles. Particularly for microscopic. Right? You can apply it to microscopic as well, but you will get the negligible wavelength there. Right? The de Broglie wavelength associated with the macroscopic particle will be negligible. That will be of no use to you. Okay? Even these results were done. If a charged particle is accelerated from rest by applying potential, de Broglie's wavelength associated with the charged particle is calculated like this. And for an electron, lambda is equal to 12.27 divided by under root of V angstroms. This V is not velocity, it is the potential difference at which electron is accelerated. Right? It is the potential difference at which the electron is accelerated. One simple question. Can you let me know in the chats what should be the answer of this question quickly? Quickly, guys. If the kinetic energy of a proton is increased 9 times, the wavelength of the de Broglie's wave associated with it would become simple. Lambda is equal to h upon under root of 2mq multiplied by v. Right? Or instead of qv, let me write kinetic energy. Perfect. Let me call this as lambda 1. Now, as per the question, what we are doing? We are increasing the kinetic energy of the proton 9 times. Right? We are increasing the kinetic energy of the proton 9 times. So instead of Ke, I am writing 9 times kinetic energy now. Let's assume the de Broglie's wavelength associated now is lambda 2. Right? Calculate lambda 2 divided by lambda 1. Lambda 2 divided by lambda 1. What you'll observe? What you'll observe? You'll observe it as, you'll get it as 1 by 3. Perfect. So lambda 2 comes out to be lambda 1 divided by 3. Perfect. So that is the answer of the question. This is simple. Nothing to do with this, right? If you make this 9 times, there is a root. A root of 9 is 3. So 3 comes out. So it becomes 1 by 3 times of initial wavelength. Right? There is no such big deal here. My dear students, there is one more thing. Now, before solving the other questions, we are going to associate. We are going to associate de Broglie's concept with Bohr's model. We are going to exactly associate your de Broglie's concept with what? With your Bohr's model. Since if I talk about an electron, let's say this is the nucleus, right? This is the electron which is revolving around the nucleus. This is the electron which is revolving around the nucleus, right? Now, electron, as per Bohr's model, electron is a particle. Electron is a particle which is revolving around the nucleus, right? But you know, any particle having certain mass moving with certain velocity, there will be a wave associated with it. There will be a wave associated with it. So when the electron is moving around the nucleus, definitely there will be a wave associated with this particular electron, which is something you call as de Broglie's wave. Perfect. Which is something which you call as de Broglie's wave. Right, guys? Now, my dear students, we are going to derive one very, very, very important result. I'm relating basically de Broglie's concept with Bohr's model. Bohr suggested that the electron is a particle, right? But few minutes back, we got to know every single particle has got wave nature as well. So electron, when it moves around the nucleus, it will be having the wave nature as well, right? It will be having a wave nature as well. Now try to understand few things. See, as per Bohr's theory is concerned, you know MVR is equal to NH upon 2 pi. MVR is equal to NH upon 2 pi. And few minutes back, you got to know lambda is equal to H upon P as well, right? H upon MV as well. Few minutes back, you got to know lambda is equal to H upon MV. This is something which you got to know few minutes back. Okay. My dear students, if I just shuffle this equation like this, I'll take this 2 pi here, I'll write it like this. 2 pi r is equal to n h upon mv, right? So I'll be writing it like this. 2 pi r is equal to n h upon mv is something which you call as lambda. This is one amazing result which you got from here. 2 pi r is equal to n lambda. 2 pi r is equal to n lambda. This particular result explains the wave nature of electron moving around the nucleus. In this result, you got lambda. Lambda is the characteristic of wave. Right? So this particular result explains the wave nature of what? It explains your wave nature of the electron moving around the nucleus. This particular result. 2 pi r is equal to n lambda. Okay, 2 pi r is equal to n lambda. 2 pi r is equal to n lambda. If you try to understand it properly, put the value of n as 1. That means you are talking about first shell. You are talking about first shell. If n is 1, 2 pi r is equal to lambda. Lambda is the wavelength of one complete wave. So when electron, I'm talking about n is equal to 1. Guys, try to understand this particular thing. Have a look. Just a second. Have a look. I'm making you understand this particular result. You know, your 2 pi r is equal to n lambda. If I put the value of n as 1, it becomes 2 pi r is equal to lambda. 2 pi r is equal to lambda. Which shell am I talking about? I'm talking about the first shell. Let's assume this is the first shell. Right? So for the first shell, 2 pi r is equal to n lambda. What is 2 pi r? 2 pi r is the distance. 2 pi r is the distance covered by the electron in one revolution. Right? It is equal to lambda. What is lambda? Lambda is the wavelength of one complete wave. Right? Lambda is the wavelength of one complete wave. Imagine it like this, just to make you understand. Imagine if you open this circle. It becomes a line. If I ask you, what is the length of this particular line? You'll say 2 pi r, right? You'll say 2 pi r. How many lambdas did I get over here? I got 1 lambda. That means 1 wavelength. Perfect. That means over here, you are going to represent one wave like this. What does it exactly mean? It means that number of waves. In the first shell, you are getting one complete wave. In the second shell, you'll get 2 waves. In the third shell, you'll get 3 waves. In the fourth shell, you'll get 4 waves. So there is one important result over here. Number of waves made by the electron. When the electron revolves around the nucleus, it's always equal to n. If the electron is in first shell, it will make one complete wave. If the electron is in second shell, 2 waves. Third shell, 3 waves. Right? So in the second shell, it's going to be 2 lambda. In the third shell, it's going to be 3 lambda. Fourth shell, 4 lambda. Which categorically says that whatever is the shell number, same is the number of waves made by the electron. Right? Perfect. So from this particular result, what are we concluding? We are concluding the wave nature of the electron revolving around the nucleus will be dominating from this particular thing. When you related your Bohr's theory with the de Broglie's concept, you got to know when the electron revolves around the nucleus, its wave nature predominates. Its wave nature dominates basically. So let's try to see certain questions. Can you solve this particular question? In the hydrogen atom, if x is the radius of the first Bohr's orbit. So you have got the hydrogen atom whose z is 1, right? Radius of the first Bohr's orbit is x. Perfect. Is x. Right? If the radius of the first Bohr's orbit is x, what does that mean? That means r0 n square divided by z is equal to x. R0 as such, n value is 1, right? Because he's talking about first orbit. Z value for hydrogen 1, so r0 is x. R0 is x, right? You got the value of r0. Now, de Broglie's wavelength of the electron in the third orbit. When the electron is revolving in the third orbit, what will be its de Broglie's wavelength? Right now, I give you one result. 2 pi r, radius of electron in the third orbit, is equal to n lambda. So it's going to be 3 times lambda, right? 3 times lambda. So it's going to be 2 pi as such. This is going to be r0 n square. N square is 3 square divided by z. Z for hydrogen is 1. It is equal to 3 lambda. So 1 of 3 got cancelled, right? So it's going to be 2 pi. Instead of r0, you are going to write x. Instead of r0, you are going to write x, right? This is 3 2s are 6. Perfect. So 6 pi x is equal to lambda. This is the answer of the question. I believe you can solve it. Right? 6 pi x is equal to lambda. Perfect. So guys, I think this much is enough for today. Perfect. Next session is going to be the last session of atomic structure, in which I shall be discussing the Heisenberg and the quantum mechanical part, right? Your quantum numbers, etc., etc. Okay, I believe this much is enough, and do let me know in the comment section of the video if you actually liked the session or not. See you all in the next session. Next session is going to happen day after tomorrow. Day after tomorrow, we shall start with the Heisenberg's uncertainty principle, and eventually we'll move into the quantum numbers as well. Okay? Hello guys. With this, taking leave. See you in the next session. Do let